mini symposium today. Again, it's sort of a mix between weather, climate, fluid dynamics. Again, I'm looking forward to all of the talks, and let's just jump in. Thank you so much, Jimmy Booth from City College, to be with us today.
Hi, everybody. Yeah, I'm happy to be here, seeing you all and chatting about this stuff. When Tobias asked me to give the talk, I originally just thought about climate and weather, but then when I saw the other titles in the mini symposium, I changed my title. So here we go. I'll also say I didn't know exactly the target audience, so I worked with the PhD students in my group to kind of figure out a place to put it, where someone who is studying other elements of physics will get a little bit of background, and hopefully it's not too boring in that respect. I'll point out V, because he's here as well, and some of the work I'll present was stuff that he did with me. And then we have some other collaborators, recent and then others that I worked with about 4 years ago. And I just want to say in the beginning, if you think about atmospheric science and what people are doing in atmospheric science, you could group them into these 3 spheres. And more recently, I have been sitting farther away from the theory side, and I was really excited about giving the talk in one respect, which was I really want to get back into it. I have a master's from a pure math department, and I really want to go back and give a talk there. And to do that, I need to boost back up the amount of time I'm thinking about theory. I also wanted to start the talk with a movie, and the hope is that this would just give everybody something pretty to look at while I talk. All right, so I generated these images. On this side over here, we're looking at height anomalies, and I've intentionally blocked out the North Pole so that if you squint your eyes, you can see a rotating fluid tank. And on this side over here, we're looking at the actual precipitation simultaneous with these vortices moving around. The vortices, you can see, they tend to always move west to east, but there is also north-south movement in them. The blues we think of as negative height anomalies, and we call them cyclones in atmospheric science. The reds we call anticyclones. And these coherent vortices are an amalgam of a lot of different waves. So you have multiple length scales of waves interacting, creating these vortices. And then in places where the blue vortices get quite intense, that will correspond to places where you have really heavy precipitation, which on this side is shown by the darkest red. In this particular example, I will also just mention November 30th, 2012 was when Superstorm Sandy hit New York City. And so this big blob here is Superstorm Sandy. And the reason it was super as a storm was actually because you had a tropical cyclone, which is a hurricane, interacting with an extratropical cyclone and an extratropical anticyclone. So this red blob here and blue blob here are 2 very coherent vortices that contrived to force the precipitating region and the windy region of Sandy directly inland. And it was that path that really made Sandy so dangerous. All right, so then back into the slides. And what will I talk about today? So I'll give a definition of terms, and then I'll talk about some global changes in storms and the jet from theory and climate models. And then I'll look at some cold season extremes from idealized numerical modeling, and then some warm season extremes from observations and climate models. And then a very short discussion to conclude. Because I was trained as a mathematician, I like to start with the definition of terms. So I define my terms here. All right. From my title, we've got the geophysical fluid dynamics being fluid dynamics with rotation and stratification. Climate change is the human-driven increases in greenhouse gases, which is leading to increases in the global average annual temperature, and then all of the little changes that are happening with that. And then weather extremes will be heavy precipitation, severe winds, prolonged heat events. For me, all the focus is on the mid-latitudes. There are weather extremes throughout the globe, but these are the ones I study. Getting right to the point, will anthropogenic climate change lead to more extreme weather? Yes. All right. And if we want, we can take as a case study the flooding in the Northeast US that occurred on August 31st. And in this image up here, we're looking at the water vapor imagery from satellite, and it's just emphasizing a huge amount of water vapor moving poleward. And then in this figure down here, they're showing the accumulated precipitation associated with this event. It was particularly damaging because we had over 3 inches in a single hour. And so how do you get all of that rain falling? Well, you have a lot of water vapor in the atmosphere, and then we can bring it back to theory. So from thermodynamics, there is the Clausius-Clapeyron relationship, which says your change in your saturation vapor pressure as compared to your change in your temperature has a scaling such that it's raising, the saturation vapor pressure raises exponentially with changes in temperature. Now, since the Earth is mostly covered by water, if we raise the temperature of the Earth, there's going to be ample water to evaporate. And so the relative humidity in any given part of the Earth is going to be nearly constant in the future. So what we'll see is increases in temperature leading to increases in water vapor in the atmosphere. And so if you don't change the dynamics of the atmosphere at all, because of the increases in temperature and increases in water vapor, the probability of larger rain events increases. So yes to extreme weather, unfortunately. Stepping way back now and saying, what does the atmospheric circulation look like in general? We can do something like this, where we draw the Earth and say, okay, it's warm in the tropics, it's cold near the poles, and the general circulation is surface easterlies, so winds from the east in the tropic, and then surface westerlies in the mid-latitudes. And then if we looked at a cross-section of the most important circulation, you have upward motion near the equator, and then outward and downward motion in the subtropics, and then circulating back in. This we refer to as the Hadley cell. And then next to the Hadley cell, you have a maximum in the winds blowing from west to east. That's shown in the gray here. That's our jet stream. And then on the poleward edge of the jet stream, you have your cyclones. And I'll get into more detail about what we mean by those. I note very carefully that the vertical cross-section here is way out of scale. So vertical motion and vertical length scales in the atmosphere are teeny as compared to horizontal length scales. And that allows us to do a lot of good and useful simplifications of our equations when we're thinking about them. But I point this out early on because we're going to be interested in these cyclones because that's what's generating the weather extremes. And it turns out you get a lot of communication from the tropics that influences the variability in it. Okay, I'm also going to talk a lot about numerical models and numerical model results. So I wanted to define these, and I wanted to give an equation that should be familiar to everybody in here, our Navier-Stokes equation, and then note that the momentum equation for the atmosphere is the same thing, but now we're observing from a rotating framework. And because of that, we have 2 new terms, right? So we still, let me first also mention this big D, that is what we call a Lagrangian derivative. And there you get your acceleration and your advection combined into one, right? And then the other terms are your pressure gradients and the influence of gravity. And then this new term, which is the Coriolis acceleration, and then the centripetal acceleration, and then friction, which we can never ignore. Now, the Coriolis acceleration and the pressure gradient force, if we use scaling arguments, dominate in the mid-latitudes at around 5 kilometers. And so these 2 terms balancing each other give us an approximation of what the winds are doing, and we'll talk more about that. In terms of solving these equations, you need numerical models, right? And so there are 2 flavors of models in the atmosphere that are regularly used, a numerical weather prediction model. And anytime you're looking at a weather forecast, you're getting that from an NWP model. And these are solving the minimum equations. They also have to solve thermodynamic equations. And the equations are coupled through this pressure and density term. And the ocean is like a prescribed boundary condition for these models. And then separately, you have general circulation models, or GCMs, which you'll also hear called global climate models, and both work with the acronym. And these models were designed for climate projections. They have a dynamic ocean, and they simulate their own weather. They are not reproducing exactly the weather that is happening on one day to the next, but they're reproducing the same type of weather. And the models up till recently were very different in terms of their spatial scale, but they're starting to converge. And in fact, in 10 or 2 to 10 years, you will hear much more about a single unified model that can be used both for weather forecasting and for the climate projections. More background. So what do we know about climate change so far, and how does it separate if we're talking about thermodynamic changes and dynamic changes? And is Ted at Reading, Georgios? I know he's, yeah. Okay.
Reading it's 4, yeah.
All right. And so I'm going to lean heavily on one of his papers just because it has some nice examples for thinking about this stuff. So here we're looking at the globally averaged annual temperature. So take the whole globe, average it, and then say, what was it? How does it change with respect to an average during a period from about 1940 to 1970? So this is like our baseline, and that's why the anomaly is around 0 then. And then you see prior to the baseline, things were cooler. And then after the baseline, things have been warmer. So there's a clear signal of warming. And if we ask how much sea ice is covering the Arctic at the end of the summer, there we see a decreasing trend. This one doesn't go so far back in time. Prior to the satellite era, didn't have a good measurement of that. So our thermodynamic variables are changing, right? But if instead we say, well, has the dynamics been changing? And one of the things we can look at, referred to as the Southern Oscillation Index, is it's the difference in pressure between an island in the Pacific and then Darwin, Australia. And that pressure difference gives you an idea of how the dynamics of the tropical Pacific is varying. And what you see there is not a lot of trend, right? There's a lot of variability, but there's no long-term trend. Similarly, we could take all of the precipitation that falls on India during the monsoon season. And again, we have a really nice long record of this, and there's not a clear trend. And so the question is why? And it's nice that we're all here talking about fluid dynamics, so I can just say, well, fluids are complicated, and so the dynamics are complicated. And the other big point is that the natural variability, so factors other than anthropogenic climate change, can lead to big swings in these. And so we have a signal to noise issue here, where the signal is small as compared to the noise, which is the natural variability. But we can get somewhere with this stuff if we start thinking a little bit more about the phenomenon we're interested in. And the phenomenon I'm interested in today is baroclinic instability. And that's the instability that's going to arise anytime you have a rotating fluid that's stratified, meaning not just a single layer, and it's subject to a horizontal temperature gradient. In this figure here, you have longitude and latitude, and it's warm in the subtropics and cold up in the poles. And that temperature gradient sets up an instability, and the response of the fluid is to make these wave-like structures. And you can see it in the temperature field as warm air fluxed poleward, cold air fluxed equatorward. And so the response to the instability is to wipe out the gradient, right? Nature abhors a vacuum, and that's what we've got going on in the atmosphere. Why is it shaped this way, however? That's related to the rotation of the Earth. And I hit on that more a little bit later. If we look at the pressure gradients, pressure anomalies associated with this motion, you have these blues, which would be our cyclones that are mentioned earlier, and these reds, which would be our anticyclones. And the idea is that these things, the cyclones, are more intense but smaller as an anomaly. And these are the locations where we have the stronger winds and the precip that leads to the extremes. The energy source for the baroclinic waves is the vertical shear of the east-west wind. So we take our east-west winds and we get a gradient with respect to height, and we actually can get a scaling. This is called the eddy growth rate. It's based on a simplified solution to the momentum equations in a channel with rotation. And this n term is your vertical stability. So there you're thinking about how does the temperature change with height? And the idea there is there's vertical motion, and the more stable your atmosphere is, the harder it is for that vertical motion to occur. The other thing to mention is that if you were to just look at satellites, what these baroclinic life cycles look like, it would be something like this. But I said in the beginning that we're interested in Rossby waves, so what's the link? And the idea is that during a baroclinic life cycle, you have an initial linear growth phase. And during the linear growth phase, there's a lot of lower tropospheric Rossby wave activity. So you're generating Rossby waves, and these Rossby waves are actually propagating upward in the troposphere. Your north-south temperature flux is maximum during this phase. And there is also momentum that's being fluxed upwards. When the storm hits maximum intensity, it looks something like this. And the maximum, the Rossby waves begin breaking, and you have nonlinearities that are affecting the flow, and the heat flux is actually weakened. And this kind of life cycle actually was really well documented by someone else at Georgios' school. So this came out of a paper by a guy named Thorncroft, working with Brian Hoskins. And he's now at SUNY Albany, so up the road from me. Rossby waves, all right? So the fundamental number in geophysical fluid dynamics is the Rossby number, all right? And it is giving us a ratio of the horizontal motion to the influence of rotation, or if you want, it's an acceleration scaled by the Coriolis factor. And what's great is that way long ago in Time magazine, which the young kids have never even heard of, I'm sure, but there used to be this magazine, Time magazine, that would show up at your house, I guess, for some of us. And this, when they covered Rossby, they actually let him include an equation in the magazine. So I think it's a great thing to mention. Here is just kind of a schematic showing these like wave-like motions. And then the idea is that you have a baroclinic life cycle, which gives you this hook-like thing. And the waves are sitting within it and evolving with it. All right, so that's my definition of terms. And now we'll get into global changes. And for that, we're gonna step back and look at a really broad brush picture of baroclinic wave activity. And in this figure here, you have these two maxima in this field that I'm plotting, which is the variance of a time filtered wind field. So we isolate the timescales at which weather occurs, which is a 2 to 6 day time scale. And then we just plot the variance of that field, and we get these local maxima. This, in climate parlance, is called a storm track. And so storm tracks is this term that's totally misappropriated, and the people who coined it even apologized for it, and they said we should have called it baroclinic wave activity, but it's too late, it's in the literature, so it's storm tracks, right? And then on this side, all we're plotting is the wind blowing from west to east at a long-term average during winter. And you can see there's maxima in these winds in certain locations. This we're going to call the jet stream, all right? You can fly across the US, and when you're flying to the West Coast, they're always saying it's going to be a little slow today because the jet stream is strong. You're flying back to New York, they say, oh, it's going to have a real short trip because the jet stream is short. What they're actually talking about in atmospheric science parlance is a jet streak, and a jet stream is only what we get when we do a long time average. What we can see in the figures, though, is that the jet stream maxima and the storm track maxima are offset from each other. And this relates to the fact that these the baroclinic waves grow on the poleward side of the jet. And it's really just a place where you have a strong amount of poleward shear in your westward flow. Why are these located where they are? Well, I introduced before this ED growth rate, right? And we can go back and actually plot the ED growth rate, and we actually find this maximum that corresponds to the region where our storm tracks are growing. And you say, okay, well, that's kind of prescriptive. Why is this so strong here? And it comes back to something a little more simple, which is the fact that you have a equator to pole temperature gradient that's driving the winds from west to east, and then they impinge upon these mountains, and the mountains deflect the winds. And so the contours here are just showing us lines of constant pressure. And then imagine that as a stream function. And so the flow is moving parallel to the lines of constant pressure. And so your flow is moving west to east, following these lines. And this is your long time average of the circulation. And then the anomaly in these fields is what we're calling the stationary wave. And the stationary wave is driven by this deflection of the mountains. It's also dependent on what your tropical heating looks like, and then your land-sea contrast. So all three of those factors come into play in kind of setting the position of the stationary wave. The stationary wave is projected to change with climate change. However, our exact knowledge of how it changed is something that we're still working on. But what you can see is that the stationary wave is concentrating regions of tighter pressure contours. And so that's where your jet is the strongest. And then the jet being strongest translates into the region where you have your maximum in the ED growth rate. That's where your baroclinic waves can grow most frequently and most rapidly. The eddies themselves also feed back onto the jet, right? And so the baroclinic wave activity, can be approximated as eddies, and then we can derive something that tells us about an acceleration of the flow due to the eddy terms. This is referred to as the E vector. So here we're plotting with the arrows, the E vectors, and you can see they're strongest within these storm track regions. And then we can see where we have divergence of the E vector, we're actually strengthening the mean westerly flow. And where we have convergence, that's where we're weakening the westerly flow. Okay, so how will the storm track and jet stream change with climate change? So if we go back and remember, okay, so most of the flow in the atmosphere has a small Rossby number, and therefore the Coriolis term is dominating. We can think about the winds as just being geostrophic winds, and therefore they're flowing parallel to our pressure contours. And then if we look at the difference between the geostrophic winds at an upper level and a lower level, we refer to that as the thermal wind. And this difference in the strength of the wind relates to the temperature gradients. And so here, I actually just picked out the weather forecast map from 2 days ago. And this is plotting the temperature here. And then this is plotting the strength of the winds here. And the point is that where you have a local maxima in your surface temperature gradient corresponds to also where you have the strongest winds aloft. And so this thermal wind relationship is just it's derived just by a combination of understanding of thermodynamics and geostrophic wind. And it tells you just diagnostically that the stronger the temperature gradient, the stronger your winds aloft, where aloft means about 10 kilometers above the surface. Now, in the current climate, we know that the summertime jet is weaker than the wintertime jet, because in summertime, the north-south temperature gradients are weaker than they are in winter, right? In summertime, the pole is receiving radiation, the whole region is warming up, and so your north-south temperature gradient weakens, and therefore your thermal wind strengthens, so your jets are stronger in winter than they are in summer. And so is the future going to be more summer-like? Presumably, right? Things are getting warmer everywhere. So maybe we just say, all right, use thermal wind, we say the jet is weaker. But it gets a little complicated, unfortunately. So now what we're going to do is we're going to take information from a climate model and we're going to average it over all longitudes. So we're plotting what we call the zonal mean. And so imagine you're positioning yourself on the Greenwich Prime Meridian and you're looking at the atmosphere and you're observing it and you can see all latitudes and then you're looking at it versus height. And then what you'll notice is that the change in temperature with warming is not isotropic. And instead, there's local maxima. There's a local maxima in warming in the upper troposphere in the tropics, and then another one in the Arctic. This warming in the tropics, we understand actually, because as the atmosphere warms overall, the vertical gradient in temperature approaches something that looks more like a moist adiabat, meaning moisture has a bigger role in setting what your temperature gradient looks like. And that translates to more warming above than below. This warming, we also understand, you might have heard of it, it's called Arctic amplification. And that disproportionate warming of the Arctic is due to the fact that we're exposing more of the ocean. So there's more heat fluxes and more moisture fluxes. And so you have feedbacks from the sea ice melting, amplifying the warming there. There are the interesting thing for our conversation about the thermal wind is that Arctic amplification is weakening the north-south temperature gradient. And so that would mean weaker thermal wind. But the upper tropical troposphere warming more than its corresponding polar regions strengthens the temperature gradient and strengthens the wind locally. And so down here, we're plotting in color the change in the winds blowing from west to east. And you see this amplification of the winds up near the top. And so unfortunately, the thermal wind argument doesn't work because of this big change in temperatures in the upper regions of the troposphere. Let's see, other things to mention here. No, I think that's okay. Now, instead of using theory to talk about how the storm tracks and jet stream will change, we'll try and use models. You might have heard of CMIP. This is the Climate Model Intercomparison Project, international project where multiple modeling centers use the same set of atmospheric changes to run their models into the future. The atmospheric changes are referred to as representation. I don't think that's right at all. Representative concentration pathways. and the idea there is that we have an idea of how population is going to change. We have an idea of how fossil fuel use is going to change. And we use that to make projections of how concentrations of greenhouse gases change in the future. And then modeling centers integrate their climate models forward in time, prescribing these changes. And then the data from the climate models are made publicly available for anybody to analyze. And so I'll show you results from folks who didn't run the models themselves, actually. As a side note, these climate models, if you will, just have two primary principles from physics. The first law of thermodynamics and then Newton's second law. And that's it, right? That's all we need. So now what are we going to look at? Okay, so I introduced to you all the storm track and then the jet. And now we're going to look at the change in the storm track and the change in the jet. So red in this figure indicates strengthening in the future, and then blue indicates weakening. And we're actually going to look at the results from 2010 climate models, 2015 climate models, and then 2020 climate models. And overall, you can see the pattern doesn't change that much. However, there are subtle changes that are important, and so progress is being made. We also see that for the storm track, there are a lot of regions where the storm track weakens, and then a few regions where the storm track strengthens. And then meanwhile, for the jet, we're seeing a strengthening of the jet in some regions and a weakening in others. And this is actually really interesting. This is, we have this feeling like, oh, the strength of the jet and the strength of the storm track have this nice one-to-one link. But in fact, there's more than that going on. And these results actually suggesting a lot of weakening of the storm track give you an idea that, okay, the surface temperature gradient might actually be more important than the upper level temperature gradient for these storms. The other thing to highlight, however, is that these changes are typically only about 5 to 10% of the mean fields, right? And so these changes are not huge. So it's modest changes in the storm track and the jet, strengthening in some places, weakening in some places. Now we'll step back to this Shepherd argument about changes in dynamics versus changes in thermodynamics and our uncertainty. So on this side, we're plotting in shading the change in temperature 100 years from now with the present day. And then the stippling is indicating everywhere that the multi-model mean has differences that are at least 2 standard deviations larger than natural variability. So this is saying all of these changes are significant as compared to the noise of the natural variability from year to year changes. For changes in precipitation now, things are not as clear. Again, the stippling are places where the changes are significant as compared to natural variability, but the hatching are places where the changes are not significant as compared to natural variability. And so we're seeing a lot of places where the models are suggesting something's happening, but we can't disentangle it from what just happens in the year-to-year changes, right? And so this comes back to this idea that for something like precipitation that relies on dynamics, there are still a lot of places where the signal is not large as compared to the noise. Are the climate models improving? Yes. And this now is showing us shading is the difference between the models and observations. And going from the 2010 models to the 2020 models, the shading decreases, especially over in this region. And so there's this tendency to agree that the models are improving at dynamics, but you can also see there's still error. And in places where the error is 1, that's places where the value is something like 4. So it's like a 25% error. So more work to be done. All right. So now shifting gears, I'm going to talk a little bit about idealized numerical modeling of baroclinic waves. So here we're going to go back and we're going to use a numerical weather model. We're going to simplify the conditions so we're just in a channel and we specify an initial jet and then we let the baroclinic wave or the baroclinic life cycle evolve. And if we look at the time evolution of the baroclinic life cycle, it's something like this, where you have the contours showing you sea level pressure. So deepening of the sea level pressure translates into a strengthening of the storm, increase in size, and then also the shading showing you precipitation shows you an increase in precipitation. Don't worry about the color of the different precip. That's for a different talk. So how will the atmosphere that influences the storm change with global warming? We've talked already about how the surface temperature, the gradient in surface temperature is supposed to decrease, so a decrease in baroclinicity. And then our low-level atmospheric water vapor is certainly going to increase. And this is a secondary energy source for the extratropical cyclones, so it could intensify them. And then the actual lapse rate is moving closer to a moist lapse rate. That's beyond what we need to talk about in this class, this lecture. All right, do the climate models capture these things? Yes. Shading now is what we've seen before, where we have amplified warming in the tropical troposphere here, amplified warming in the Arctic, and we're going to focus on this amplified warming weakening the north-south temperature gradient. And then shading over here is showing you the change in water vapor, and everything is getting more moist, so we're moistening the atmosphere. So the research question here would be, how are the wintertime storms changing with climate change? And what are the sensitivity of the baroclinic waves to changes in surface temperature and changes in atmospheric moisture? Here's our initial conditions. Again, we're staring from the Greenwich prime meridian at the atmosphere in cross section. Closed contours are showing you the strength of the wind. So this is our jet maxima. This black line here would be separating the troposphere from the stratosphere. Shading, or the horizontal lines here just showing you temperature. And now if we look at this cross section right here of the winds, then the black is showing you current conditions. And then we're going to change the model to force it with much stronger jet or much weaker jet. And then we're going to look at how the storms respond. And then we're also going to do other runs where we fix the jet in this black condition, but then we're going to change the overall temperature of the atmosphere. And so these changes in the bulk temperature of the atmosphere, because we're changing them everywhere, are not changing the baroclinicity. All they're doing is just making the atmosphere moister because we're keeping the relative humidity fixed. All right, now we're going to look at results in terms of the time evolution of sea level pressure on this axis, or time evolution of the eddy kinetic energy on this axis. So the bottom is always showing us eddy kinetic energy. The top is always showing us sea level pressure. In this top case, this is just kind of verification that our model makes sense because we ran these dry. So we first run it with no water vapor at all. In that case, you change the baroclinicity and you see a response to the storm. The response is telling us the maximum in eddy kinetic energy is increasing, and also the timing of intensification is earlier. In this case, because all we're doing is changing the bulk temperature, we see almost no change, right? And this is what we wanted. Now, on the bottom, we're going to make the changes with water vapor present. And again, changing baroclinicity leads to an intensification of the maximum EKE, and the storm is, or the life cycle is developing faster. So we have a faster development and a bigger maximum when we increase baroclinicity. Increasing temperature instead leads to the storm developing faster, but the overall EKE goes down. Why is that? Oh, I decided to take that figure out. It's that way because the storm itself is contracting. So the overall spatial scale of the storm is becoming smaller in the horizontal and larger in the vertical. And what this is that as these baroclinic life cycles develop, you have a lot of Rossby wave activity and upward motion. And the amount of upward motion you have depends on how much convection is in the system. And the more water vapor you have, the more convection you have. So you're basically getting an offset where you're getting storms that are taller in the vertical and smaller in the horizontal. Let me check my time. Okay, great. So now let's talk really briefly about warm season extremes. All right, so atmospheric blocking is the phenomenon in which we have persistent mid-latitude anticyclones. So in this case, for an anticyclone, you actually have convergence of wave activity in a region, but then it doesn't propagate out of the region. The waves break. And in a wave breaking situation like that, you actually have, you can form a giant anticyclonic vortice that slows down the jet. And that's the reason it's called a block, because it's blocking the west to east flow. If we look at the multi-year average of where blocks usually occur, you can pinpoint them as being at the eastern edge of the ocean basins. And so over here, this is the Atlantic Ocean Basin. Over here is the Pacific Ocean Basin. I always find Florida on these maps and then orient myself around that because it's just so weird looking, it's easy to find. The contours here are again showing us the jet stream. So just like we had a link between a jet stream and a storm track, we have a link between the storm stream, the jet stream, and the blocks, where the blocks tend to most frequently occur at the end or terminus of the storm track region associated with a jet. So it goes jet, storm track, blocks. These blocks, because of their persistence, can lead to extreme events, right? They can force cyclones into paths that they don't normally take and create havoc for that reason. They can also force the storms to move very slowly, which can lead to persistent winds in one region, which can lead to flooding. And then in summer, if these blocks get stuck in certain places, they can amplify locally, which leads to more radiative warming and local heating. And that's what happened this last summer, where there was an extreme event in the Pacific Northwest that was due to a block. Why are blocks located where they are? So V carried out a set of analyses where we took a climate model and we simplified it to where we didn't have anything but an ocean. When we do that, we call that an aquaplanet. And then we synthetically add some orography. So it's a mountain-like structure. And when we put in the mountain-like structure, we can then integrate the model and look at where blocks occur. And in the case where we have only one mountain, which is this avocado-shaped thing here, you have a jet maxima downstream of the orography, which makes sense from the deflection of the winds that we talked about earlier. And then the blocking maxima sits way over on the other side of the mountain. And so actually it's related to the deflection of the winds as well. So the mountain deflecting the winds preferentially generates more anticyclonic motion in this region that reinforces and seeds the blocking region. If we put in two mountains that are at a symmetric distance from each other, then we get two jet maxima and we get two block maxima. It's interesting to note that these things aren't perfectly symmetric, and that's because we haven't run it long enough yet. This is about a 30-year integration. We found that it would actually take about 150 years to get it to where this was cleanly symmetric. If we move our mountains, so now we have a small ocean basin and a large ocean basin, we again move where our blocks are occurring. And so we really convinced ourselves that the orography and the deflection of the west to east wind, or the deflection of the jet, which is another way of saying the stationary wave, has this critical role in setting your location of your blocks. What's interesting is I recently heard a talk about a hydraulic jump explanation for blocks. And that was a really neat, different parable about flow dynamics, where they argue that it's less about the turning of the winds and it's more just about slowing them down. Remains to be seen if that theory is right, but I really liked it. I thought it was a unique and different thing to hear. Last little research question I'll discuss is, what's the role of blocking in generating heat waves, and how will blocking and heat waves change with climate change? All right, so this plot here is saying for time periods that we've already had, if we identify heat waves just as exceeding the 70th percentile at each location for temperature for a 3-day period, and then we say what percentage of the heat waves are associated with blocks, what we find is that there's some signal to it, but not much. But then if we jump to where we're looking at heat waves defined as the 99th, exceeding the 99th percentile of temperature, so the most extreme heat waves, and we say what percentage of those heat waves are associated with blocks, then we see the number goes up, and that the prominence for blocks causing heat waves seems to be maximized on the over the continents, and in specifically in the Scandinavian region here. So it suggests that the blocks are really important in the current climate for generating the most extreme heat waves. What will happen to blocks in the future? According to climate models, the amount of blocking that we'll have in summertime will decrease. So the models suggest a decrease in blocking. But there's not a decrease in heat waves, right? I mean, it's just unfortunate. It's just getting hot. However, if we look at the, so this plot is the same we were just looking at. This is the change in blocking, showing a decrease everywhere. But if we look at the change in the percentage of heat waves associated with blocks, we also see this decrease, and it's basically, you know, showing the block decrease. But the point is that heat waves in the future are going to be generated partially by a different dynamical mechanism than they are in the current climate. All right. So those are the takeaways, and then a little quick discussion. I want to come back to the Shepherd paper because he shows another plot in that paper, and this he didn't focus on this for the same reason I am, but this figure is just showing us distributions, and he chose to focus in the Eurasian North Atlantic sector because that's where he lives. But he's showing distributions of sea level pressure. Gray is the current climate, red is the future climate. And we're just looking at the changes in the distributions for current climate and future climate. And the point is, all of the distributions change. However, the distribution for surface air temperature changes the most. Right? And so that comes back to his story about thermodynamics being more important or easier signal to see than dynamics. However, these changes for sea level pressure and for precipitation, and he mentions this for precipitation, they're not small, right? These changes matter and will affect our extreme weather. Here you can see an extension of the tail for positive precipitation extremes. This comes back to our story about Clausius-Clapeyron, right? So thermodynamic theory on how moisture changes with temperature gives us great confidence that you're going to have wetter events in the future. Sea level pressure, this increase in lower sea level pressure is corresponding to the increase in the baroclinic wave activity in that region. And so the dynamic signal is there as well. For me, it's kind of saying the climate models all agree that there are going to be these changes. They disagree on exactly where they're going to occur. And fundamentally, what this comes back to for the conversation that I continually have with V is what's going to happen to the stationary wave and how much confidence do we have in that? And for what's going to happen to the stationary wave, we have, well, the tropics force the stationary wave and the tropics are changing. Do we know how it's going to respond? Sort of, but the climate models, if you're saying where do they have the biggest bias, it's in this tropical circulation. And then linking nicely, I think, with the talk by Anna is the stationary wave is also dependent on what the eddies are doing. And so the changes in the storm track feedback on that stationary wave. And so we've got this coupled fluid dynamics problem that is tricky and interesting. And every time I write a proposal about this stuff, a reviewer is always like, yeah, but how are we going to deal with how the storms change the mean state? And that feedback is just on everybody's mind. So in fluid dynamics, that's just a great thing to kind of hang your hat on and think about. With that, I am finished and I can take questions. Thanks.
Well, thank you so much. Let's give a round of virtual applause, and let me see whether I can do this. Pause the recording for a second.
So let me introduce Georgios, who will talk about noise-induced transitions in climate models and comparing Brownian versus Levy noise. So Georgios is still listed as being based at the University of Reading, even though he just told me that he's now living in London, and I think he's soon going to work there, or maybe already has started. Georgios, please go ahead.
So thank you for the invitation, and many thanks to the previous speakers, who, by the way, by introducing several concepts, I can now skip some definitions. And as it is the last talk of today, I'll try to keep it as simple as possible, let's say, and make a fun presentation. So the topic is in collaboration with Valerio Lucarini and Larissa Serdukova from the University of Reading. And another topic that I'm going to also discuss here is with Tobias, Grafke, and Navier-Stokes. So noise-induced transitions in climate models. Now, I shall talk mainly for macroscopic transitions. And in this framework, I will refer to the fact that in the microscopic level and according to the current astronomical and astrophysical configurations, and I mean by the incoming solar energy, Earth can indeed exhibit at least two stable climate states. One is the present day warm, and the other one is one such as it's fully glaciated. There is sea ice everywhere, and we call it a snowball. And this is doable because you can imagine that if the temperatures drop so much that the whole Earth freezes, what happens is that there's a so-called albedo feedback, whereas ice reflects stronger the incoming sunlight, and therefore, in some sense, what this drives the system to a stable state, which is nevertheless fully glaciated. So, okay, now the first thing to start here, I mean, the easiest way to start here is by introducing the concept of energy balance model, and in the sort of easiest way to see the Earth system is by literally as a one degree of freedom. So, for instance, you see here in this really nice picture is the pale blue dot photo. This is Earth from very far in the space. If you basically see the Earth as a point and the only variable of care is temperature, then you can define this kind of energy balance model, whereas you're interested for the evolution of temperature as as driven by the two interacting mechanisms coming from the solar radiation. So one is Ri, which is the incoming solar radiation, minus the outgoing. And these two feedback, first one is the ice albedo feedback. So albedo is this alpha parameter here. S node is what we call the solar insolation, and mu is this non-dimensional parameter that is going to be very relevant later on. And of course, the outgoing feedback is the Boltzmann feedback, where the incoming solar radiation is re-emitted as thermal radiation. And just a quick notice here, albedo is typically a piecewise function. So for instance, as I said earlier, for smaller temperatures, it's higher, and then for larger temperatures, it's larger. And of course, in this very simplified example, we have like a linear interpolation in temperature. Now, if you work around this very simple system, this deterministic system, you're gonna find three fixed points, which are stable solutions. So one is this branch here, and the other is this the warm branch and the snowball branch. It's a bifurcation diagram, but where we sort of modulate this non-dimensional mu parameter. And in the between, there is this unstable branch that there is an edge state, as we're going to see later, and basically it's very it's unstable. And one way to view this problem is you can actually write it as a potential. Okay, in this form you can basically, and in this way you can view the system as in a sort of a landscape where the attractors in this case are fixed points in some regions, in some wells. They're separated by some ridges, and the point is how if you ever find yourself in one climate and you're in a deterministic case, you're going to stay there, but how can you explore this landscape in a more complicated setting? So this is going to be the target of today's talk. Before we proceed, I just want to briefly mention that the introduction of such kind of energy balance models was first done independently in the late 60s, basically in 1969, and independently by people, one from the Soviet Union, one from the US. And that was, in some sense, the first study into understanding whether, by that time, massive nuclear explosion could induce nuclear winter, which could, of course, be an even greater threat to life. And the idea is, of course, that if massive explosions occur, then increased particulate matter would be found in the atmosphere. This would in turn increase albedo. This would decrease the solar radiation, and this would sort of cause some sort of nuclear winter and would keep the system out from, you know, the present warm state towards a possibly global glaciated. So this kind of, so there was zero dimensional. The one dimensional is what I'm gonna discuss here in the first part of the talk. So the Gill-Sellers energy balance model is was introduced in the mid-70s, and now just to give you the term by term definition here, the first term here is a new term, it didn't appear before, is the meridional heat transport on the Earth's surface. So basically what we have here is, as a 1D, we have just the latitude. You have effectively averaged over the longitude contribution and the height contributions. And we have sort of projected these effects to the temperature, which is now a one-dimensional field. So is, of course, the albedo. X here is, by the way, a non-dimensional parameter, which is basically the latitude. The two other terms, so D2 is the heat absorption, is the one I showed you before, and D3 is the Boltzmann effect. So if you solve this numerically, you're going to end up again with this three solutions. And we choose here mu equals 1, 0.5, which is, by the way, what I'm going to use later on in this presentation. So if you solve this numerically, you get this profile of temperature as a function of this parameter x. So for 0, basically, this is the equator, which you see it's like warmer. Temperature here is in Kelvin. And the poles are, of course, colder. And this is the distribution of the warm state. This is the distribution of the edge state, the unstable one. And this is the distribution of the snowball state. And if you do, again, the similar plot as before for this particular model, you get a bifurcation diagram for the chosen image. So the point here is, if you find yourself into one of these stable attractors, there's no way you're going to escape. One way to escape, though, is to introduce some sort of noise into the system. And in this case, this is what we did. So this is the stochastic version of the energy balance model I showed you before, where the first term D1 and D3 stay the same, but perturbations are here added to this one-dimensional parameter mu. So mu before was just multiplying Q the solar irradiance. Now on its own, it's we add this some sort of perturbation and then we multiply. Therefore, in this form, this is not an additive, but this is a multiplicative kind of noise. So this is now, so L dot here is a stemestic alpha stable process. And I recall that for A in the open 0,2, it's a Levy process, and for A equal 2, this is the Gaussian process. And before we move on, I just want to mention that in this case, again, we have spatial, potentially infinite dimensional. It is an infinite dimensional field in 1D. Of course, later on, we sort of discretize this and use finite methods. But still, we want to do a further coarse graining of the phase space only for visualization purposes. And therefore, we have now the temperature field. We're gonna, one variable that we're gonna constantly show from now on is gonna be the spatially average temperature, so just the global temperature. And we're gonna also show a temperature gradient, which is basically the equator minus poles temperature difference. So Jimmy made in the first presentation a lot of a discussion of what temperature gradients might be in a realistic system such as the Earth. Here, of course, because it's completely symmetric, we can just take a latitudinal band around the equator and of temperature and subtract a polar band and take this observable. So let's start with the Gaussian noise. So the Gaussian noise, essentially, we're simulating a linear process. And in this case, I want to first just compare how it looks like if we look the time series of a weak signal and of a stronger signal. And of course, we just, on the first panel, we just look an evolution of this energy balance model for 80,000 years. That's very cheap to do. And we plot the global temperature. So the first thing to see is that for the weaker noise, it spends a lot of time in some attractive, and then it jumps, spends some time, and then it jumps back, and so on and so forth. This is also the time series of the temperature gradient. If you increase the noise, of course, we expect that these jumps will become more frequent. So the next thing to do, which is really relevant for this approach, is to take the signals and make basically two-dimensional histograms. So in the x direction, I'm just plotting the histogram part of average temperature and then the temperature gradient. And if you do this and just normalize the histogram, this is basically the invariant measure of the system. What's interesting to see first is that the shaded regions here, they correspond to the stochastic attractor. And this colored circle here, for instance, is the deterministic attractor. And of course, you expect that in the weak noise limit, the centers of the two should coincide. So this is a warm attractor. This is the snowball attractor in blue. And in between, there is this edge state. And the idea here is that we want to understand how transitions occur when noise is when we put noise into the system. And in this case, you see that escapes, for instance, from the warm attractor will start for instance, from here. This is the average paths, the most probable paths. So we take many transitions and we average them. And what's interesting in this case of the Gaussian noise is that because there is one single edge state, in the case of Gaussian noise in the weak limit, we expect that this should cross at this point and then go and relax to the other place. Now, the instantonic part, the escape part, is a straight line, also here from the snowball to the edge state, and then the relaxation part is this dashed line. So you see already here that this is an example of a non-equilibrium problem because you have a bistable system with a single saddle, and the relaxation and instantonic and the escape portions within its basin do not meet. So this is the first comment here. The second comment is about if you measure the permanent time. So now you sort of identify, roughly identify a basin boundary and a basin of attraction. And you want to measure how much time the system spends on average within this basin of attraction. And in practice, we just define an ellipse and we measure the time the system spends from the moment it enters the ellipse and the model it enters the other ellipse of the competing attractor. And if you take the mean of those permanent times, we know from theory that it should follow this star deviation law in the weak noise limit. So plot the logarithm versus the inverse of the square of the noise intensity epsilon. And if you fit, you get a really, really nice, if you fit and get the slope of this, now it looks like a line, you get a really nice estimate of what we call potential barriers in this project. Okay, so from this, for instance, you can already see that the warm basin of attraction is slightly deeper than the corresponding snowball. So more interesting part here is to see some animations. So in this animation here, I'm going to show you really how a realistic transition looks like under Gaussian noise. So we have the same plot as before. On the inset here, I'm showing the real-time distribution of the temperature of the stochastic temperature field as a function of x. And the stationary states are warm, I call it M now, the edge state, and the snowball. And on the background, you see this dashed line, which is the real-time temperature field moving. So let's start. We are warm to snowball, so we are over here. And you see here by most star being the fluctuations that we impose every year, by the way. We change the fluctuation once per year. Now you see a transition is occurring, and it crosses the edge state, and it really nicely collapses to the stationary solution, and then it just relaxes to the completing snowball attraction. Now let's see the opposite one. Now we're from snowball to the warm. So I repeat, we changed the move, the solar the relative solar insolation once per year. So let's see here, we are now at the snowball attractor. We expect to see some large occurrence of move, and this will sort of drive the system out of the snowball state in this case. And there it is. So a persistent sequence of large move will trigger the system out of, for instance, here the snowball attractor. And very nicely, you see it collapses. Yeah.
Can I just probably you have said it. Is this the sort of finite dimensional reduction model, or is that?
Yes.
Okay.
So this is the energy balance model, and
Perfect.
this is projected. This is exactly projected in this for visual purposes in this two-dimensional sort of phase space. So this is the global temperature. This is the temperature difference of the equator minus poles. This is relevant.
But it's only finite dimensional because you discretize, yeah?
Exactly, yes. Otherwise, the original equation is infinite dimensional. Yeah. So let's move now. So this is the Gaussian case. Let's move now to what's the differences when you instead of introduce Gaussian perturbations, you introduce Levy perturbations to the solar constant. And again, we're going to show it once per, change it once per year. So just to give you an insight of how the signals look like. Again, this is the energy balance model written, formally written. It's in one-dimensional in the continuum. In our investigation here, we used 3 different kinds of alpha. One is 0.5, another one is 1, and another one is 1.5. And please recall that as soon as alpha increases, it more looks like a Gaussian signal. So when it becomes 2, it's like a Gaussian signal. If it was 1.999, it's distinguishable from a Gaussian signal. But here, I'm showing 2 examples at the same noise level, one for alpha equals 1 and another for alpha equals 1.5. And you can see here that fixed epsilon transition becomes less frequent as alpha increases. This is the message here. So let's see again the same kind of pictures, how they're going to change. First, let's see the environment measure. So the environment measure now is again this two-dimensional histogram. And what's already quite striking is the way that the transitions occur. So now the transition is no more cross from this edge state. And in fact, as I'm going to show you later on, even this transition started from snowball to the warm climate, it seems to cross, it's actually not that close. And the other thing is that I changed alpha, okay, and essentially the final most probable path in each alpha more or less looks the same. And the idea here is that, and we know this from the literature, is that in the case of Levy noise, the exits from one Bayesian of attraction would occur through the nearest region to the Bayesian boundary from the outgoing attraction. Okay, so if I start here from the warm, it seems that the Bayesian boundary is closer to this region than going all the way up and down and so on and so forth. This is one point. And by the way, in the inset plots here, I just have the subset of the transitions. So you see basically that as dark blue here, this is only the transition start from warm and gap into snowball, and dark red, the transition from snowball and gap into warm. The other thing to notice, which is we're quite surprised actually, because there is a prediction for the permanence time under the Levy noise. And we know for infinite dimensional systems, we only have for additive noise. We don't have for multiplicative noise, at least formally. So nevertheless, we just did the same exercise. And out of coincidence, we don't know if it's just for the particular system or not, but it seems that we confirm the law that holds for the additive noise as well. So which is that the permanence time within a Bayesian of attraction is like a power law 1 over the noise to the power of alpha. And this is here, you can see even more clearly, where we take as blue the points that are, we measured them in the snowball, and as red, we measured them in the warm attractor. For versus this permanence time versus the logarithm of the noise. And if you do the fits, the fits here, you see in this table that very, very well sort of confirm this law. So for the warm case and up to the errors, they're pretty convincing. So let's see now some animations again with that are more interesting with the Levy transitions. So the first one is we are at the warm Bayesian attraction. And by the way, keep in mind that already you can see it from here, the majority of the signal, the majority of the time the system spends is within the close vicinity of the deterministic attractor, because the jumps are most likely very small. Okay, so it's not like the Gaussian, which like explores far better the Bayesian of attraction. Here it's really within the vicinity of the deterministic attractor. So if we're going to see warm, we expect to see it over here, basically not moving now. So let's see how the jump will occur for this real transition. There it is. Very quickly, we observe, yes, a kick into this move, and the system quickly jumped from this region here, and now it's very slowly relaxes. What's interesting to notice, and I'm going to show you one more time, is that is the pattern. Okay, so the pattern that the transition occurs, it does not agree at all with the edge state here, which is of course another demonstration that of course it does not it's not even close to this state. The opposite transition is the one that in the average case it seems like it's close to the vicinity of this edge state, but as you look closer to the distribution of the temperature, you're going to see that it's not. So we start at first, of course, years go by, nothing changes. We are most of the time we're at the vicinity of the district attractor. But then the kick was going to happen, and look at this. Very quickly again, system escapes, and within a few, like maybe 1 or 2 years, it has crossed the towards the other Bayesian attraction. Now this is the last. So the final comment for this part of the talk is with regards to the comment we made about whether or not, again, we are close to this edge state. And in fact, you can, so again, we had just the temperature distribution in 1D. So it's very simplified, but still you can create another observable, which is this calligraphic I here. This is the fraction of the surface that has sub-freezing temperature. And effectively, this is like a sea ice percentage. So if the system is fully glaciated, we expect this to be 100%. If it's fully warm, there's no, so all the temperatures are basically above 0 Celsius. We expect that this is going to be just 0. And now we can make a 3-dimensional histogram. This is a lot more convincing to understand that this is not just a projection that we see them here. Indeed, the trajectories, the average trajectories, just cross through this pink point here. This is the edge state, which is not the case on the bottom here, which is the left. So this is, of course, the first part. And what we wanted to emphasize here is that in principle, we can speak for many, so that the system before was just a bistable system with a single edge state. But in principle, we can speak of many attractors and many, and a set of saddle points, you know, and therefore many Bayesian boundaries, and basically have a much more complicated system. Of course, the picture that I'm showing you here is again, is taken and inspired from our intuitive, more equilibrium kind of system, you know. But still, as I'm going to show you later, it is possible to at least introduce some concepts, you know, such as Bayesian boundaries and saddle points, even to non-equilibrium systems. And just briefly want to mention the recent works by Lucarini and Bordai the previous years, where essentially they took a climate model, which is mostly an atmospheric model, and they could do the same exercise. They could, again, introduce perturbations to the solar constant. And in fact, they could for the first time use what we call the edge tracking algorithm to locate, see here, such kind of unstable states. This is not what we've done here so far. And in the previous picture, the generalization is basically to have a finite dimensional system, for instance, and introduce some kind of noise. Okay. In our case, we did it with yearly random fluctuations, and it's important to remind that the solar constant, as we introduce it, is just a single parameter. It's just a single parameter, and the way that it percolates to the rest of the degrees of freedom is what we call here a hyperelliptic diffusion process. And indeed, it is possible to and it works actually, because in some sense, it's the main driver of, you know, the incoming energy and then therefore the diffusion of that energy to the rest of the degrees of freedom. What's really important to show here that I didn't show you earlier on is that we know, at least from the works by Franklin and Wenzel, that in the weak noise limit, you can write the invariant measure here, basically the histograms that I showed you earlier on. These were part of a sort of coarse-grained invariant measure as a large deviation law, and therefore sort of associate the energy, the noise intensity with a sort of a quasi-potential function that in some sense gives the relative importance of the different basins of attraction in your system. So this quasi-potential effectively works as a landscape, and you won't see it as, of course, always we speak about the weak noise limit, but effectively the minima of this landscape should correspond to the deterministic attractors, and then this the saddles, we expect it to have as well, you know, we see for these quasi-potential, we also expect it to have saddles near the edge states. And the idea is that, as we're going to see later on, the instantons are the optimal path that connect those attractors and with those saddle points onto these basic boundaries. So now that helps me to move on to the next part of the talk, which is the exercise we did for the full climate model. So this is already published in the Proceedings of the Royal Society. It's a collaboration with Tobias, Grafke as well, Alessandro Lai and Valerio Carini. And the point here is that we want to do the same exercises for a climate model, which is for today's standards is not state of the art, but was state of the art in the 90s. So this is with a resolution of T21. This is basically 64 times 32, and with a vertical layer of 10 levels. Jimmy in the beginning introduced us with the concept of GCM, and this is the kind of climate model we're considering here. It has sort of a slab ocean. It has an ocean that it's not realistic, but it can, you know, transport heat. So does the atmosphere, and we could also here find this same two stable climate states. Now it's more interesting to see because the warm state is this one. You can see this is the sea ice in the poles mostly, and the rest is ice free, while the snowball is fully glaciated. And these are, of course, the same plots that I showed you before. This is again the distribution of temperature, of the global temperature averaged over the longitude. It just plotted over the latitude. And you can see, of course, that this is not symmetric here, okay, due to the orography that this climate model has. The same exercise you can do here. You can have a weak noise and stronger noise, same concepts as well. Now, of course, you have the sea ice coverage. It's a realistic observable that you get from the system. And of course, you expect that for weak noise, you have less of escapes, and for stronger noise, you have much. So let's do the same exercise. Let's take and plot again the invariant measure. And now you're going to see more or less a similar profile. Okay, so the invariant measure here again has this much deeper well, which corresponds to the warm attractor. Again, this point here is the deterministic attractor, and on the other side there's the snowball attractor. And the idea is again to identify transitions across those states, and basically also for sure we have two states, but do we have also one edge state or more? This is another question that we didn't know at this point. You can get a quasi-potential, very crude exercise here. Just get the quasi-potential by taking the logarithm of the invariant measure. And in this case, for instance, you see that the minimum, okay, the minimum of the quasi-potential corresponds to the global minimum. Here, this is the warm attractor, and then this is the other local minimum, which is snowball attractor. You can, of course, again measure the escape time, so the permanence time within each basin of attraction. Follow the same law that holds for Gaussian noise. Okay, so this exercise was done only for Gaussian noise, so no Levy noise for the system. And you can take, at least from this fitting, you can get the heights of the quasi-potential. So something that I didn't show you before is the following. So I'm showing all the two-dimensional projections and strange things, but what about just the one-dimensional projection, just the histogram inverted for the global temperature? Okay, so if we just neglect this and just take what would be the quasi-potential for 1 degree, okay, which is the global temperature, and we also plot the location of the location of deterministic attractions, we see this kind of whale picture that I was describing before. But here you see that there is only one, presumably only one saddle point. But as we're going to see now, this is actually misleading, because it turns out that if you just again do the previous concept, you put 3 degrees of generalized degrees of freedom, and put again the sea ice content, you see something that we didn't expect here: the fact that the escape and the relaxation towards the 2 attractors is completely different paths. So the way you're going to start here is a snowball. The way you're going to start and go to the other side does not meet at any point with your return to that attractor. So this calls for what we call as macroscopic currents. And this is an indication for stronger equilibrium conditions, which of course is what characterizes the climate as it is. So we see that the transition paths, the snowball to warm, is not the same as the opposite, but not only that, they do not even lead to any point in the configuration space. So the global thawing and the global freezing of the planet are 2 completely fundamental processes. And the idea here, where we ended up and we write in this paper, is that the dynamics get enriched essentially because of the introduction of the hydrological cycle. And therefore, this sort of alters the topography of the dynamical landscape. So let's see now, that's even more interesting to see how those transitions look like if you look at the Earth. So on the top, I have the surface temperature. Here I have the wind profile at the 300 hectopascals. I also show the geopotential and the sea ice coverage. And the first example, I am at the snowball region of attraction, and we want to see how I'm going to go towards the other attraction. So I'm here, this is this black line. Once per year, we change the solar constant. And you see when you're in the snowball, it's pretty much dead. The system is frozen, but then there's large solar irradiance, and then the system is sort of driven out of the attraction. It follows this kind of funny path. And for the first time, you see that sea ice is breaking here. So the system now, of course, is very stable. But likely, there was again a pretty large sequence of solar irradiance, and now jumped. So now jumped, and all that is left is basically for the sea ice to melt, and all of a sudden the wind profile is much more active. We don't show it here, but also the Lorentz cycle, all the typical processes of the Earth is restoring this transition. And what is left is just to relax toward the warm attraction. Even more interesting is the opposite transition from the warm. So we are warm now, and we expect, again, we expect in the Gaussian case, we just expect a persistent sequence of below present day solar irradiance value. If we see that, that sort of drives slowly the system outside of the basin. So you see here that's low, already kicked it out a little bit. And then again, it's low. This is the month and this is the year. That goes much slower, of course. Meanwhile, the Earth is freezing. And there it is again. And another pretty low value of the solar radiance. And now it's following, it's here, it's following the path of the mean path. Thank you. And you see how quickly it's coverage. And all is left is just for this to relax to the snow. So that was what would look like from, from our perspective of warm towards the snowball transition. So I'm reaching now the end of my talk, and just want to briefly recapitulate on what on the kinds of noise-induced transition for bistable systems. So for equilibrium or reversible systems, we expect that the transition are going to be the same. Okay, so this is the basing boundary, and these are the two attractors. This is one edge state, and the back and forth is going to be the same. It's going to cross from this edge. For non-equilibrium or in the reversible systems, the transitions are going to be different. Okay, and in one example, we saw that they only meet at this single edge state on the basing boundary, or they're going to be two edge states. Okay, and therefore they never meet. So this is microscopic terms. And for non-equilibrium systems that are driven by Levy noise, the point is that transitions are different and they take place with the closest basing boundary region to the outgoing attractor. So they don't even see, basically, the jump is so high they don't even see the edge state. I'm going to skip this one because it was also discussed by Tobias in the previous lecture series. And I just want to sort of end the talk with an outlook that would sort of introducing here, in the sense that effectively there is in the climate system and basically, you know, in the majority of dynamical system, complex dynamic system, a sort of multi-scale multi-stability. And what that means is that you can treat it as some sort of landscape that has further inside information that you have to zoom in, and then if you zoom into the second stage, there are further information and bistability and multi-stability. And all this can be sort of explored with different kinds of noise intensities sort of targeted for this particular problem. This is, by the way, a nice picture taken by my father from a chestnut trunk. And you see the amazing patterns here that sort of resemble the idea that there are larger attractors inside them. You can find even structures and so on and so forth. So that's what I just said. So there's apparently a hierarchy of multi-stability. There are competing metastable states within its metastable state. And in some sense, we're trying to link here climate's global metastability with the geographically localized typical elements. And just to conclude here, of course, the viewpoint is that the climate is an out-of-equilibrium complex dynamic system. I think we demonstrated that Gaussian kind of noises can play some role into exploring the dynamic landscape, but also Levy could in principle be a fantastic tool, especially for situations where you deal with dramatic changes into the system, for instance, like an asteroid impact or a volcano, a supervolcano eruption. These are dramatic effects that sort of kick the system out of steady state. We also saw that global transition can occur by different channels, and we sort of introduced the concept of carriers of multi-stability. So this project was with the Levy noise was basically submitted earlier this week, and the rest you can see. Thank you for all for your attention.
Yes, thanks a lot, Georgios. Let's thank the speaker. It is still weird after all those years. Are there any questions from the audience?
I have a few, but if anybody else wants to go first, then
I'd love to try and think about how it spends more time in the warm state than in the snowball state. And especially nice to see that that was true in the simple Sellers model, and then also true in the GCM. Very interesting. Do you have an explanation for that?
So the thing is, I don't really have an explanation. I mean, it has to do, of course, with the choice of the parameter mu. The parameter mu, which is the sort of showed here, the relative is the relative solar radiance. So you can see here, for instance, if you see, if you look at the bifurcation plot, depending on what kind of move, so this is the factor here, depending on what kind of choice you make, you sort of changing the effectively you're changing the quasi potential, the dynamic landscape topography. So we chose, for the energy balance model, we particularly chose so that the two wells are symmetrical. But of course, if you take mu to be smaller and smaller, then that changes. Okay, so mu is basically a bifurcation parameter that can change this height. And of course, at some point, if you take quite small enough, you're going to have only a single basin, so only snowball. Or if you take it large enough, you can have only a single basin, which is going to be the worm. But it was really nice comment because indeed for the real model, mu was 1. So it was really from present day conditions.
Got it. And so do you think of it, have you been thinking of it in terms of these transitions in terms of, I mean, I totally get it for the GCM, the water cycle comes in and matters, but in the idealized model, are you thinking in terms of asymmetries in the strength of the feedbacks? Or I guess this is a different question about I guess I should say the simpler question is the transition time from one to the other equivalent? The time going from one state to the other the same?
Right. So again, this depends on mu, but this is the
I've got too many mu questions, I see.
But for sort of present day conditions, because this is what this choice of mu for the particular model and particular choice of parameters simulates, you can see that indeed the system spends more time in the warm basin for the simplified model. And we didn't go towards more detail until doing a specific investigation as to why this is happening. But effectively, another thing to notice is that basically the basin here is much smaller, and the dynamics are a lot more poor, let's say. So it's just a fixed point attractor here, and it's not much happening. Of course, that's different for the real climate model. But here you can see that at least for the Gaussian case, the system has a bit of a richer dynamics when it is on the warm state. So it's also the basin of attraction is much larger. So it could be this.
Great, thanks.
Dynamically speaking. Thank you.
That's awesome.
But just one comment towards Jimmy, because you mentioned it. In the second part, you mentioned several indications of blocking events, which was really interesting. And from this point of view here that we introduce, in particular, it could be as if you're studying a sort of bistable system, blocking, no blocking, and how you transition from this for noise-driven setting. This could be, for instance, something that we're also discussing with Valeria. For follow-up onto this.
That's a great point.
Basically, this is a more geographically, a deep inside the system. It's not just macroscopic.
Agreed. Yeah, no, that's right. I think that's a great point to think about.
Gulf Stream and no Gulf Stream.
Exactly.
Yeah. May I also ask a question though? Maybe a higher level question is, so you were initially talking about this original motivation of nuclear winter, the forcing being on the solar constant. Is that realistic in any way? I mean, maybe the argument is that you are envisioning some kind of disaster or so that darkens the sky. Would it lead, I mean, do you know quantitatively whether that's somehow realistically achievable?
Exactly.
The kind of need?
Yeah, so I'm not really sure, because indeed those, okay, from the sun, of course, it's completely unphysical, the fact that we put that kind of perturbation to the solar content. Of course, you can think of effectively, cloud covered, particulate matter covered. I'm not sure of the realism for the particular Winger, nuclear Winger equation. But the point is that for the Levy kind of noise, you see that it's, at least in my perception, it's even more relevant to sort of describe such kind of cataclysmic events, because if they happen very quickly. So it's not like, because the Gaussian case, as you notice, it just has to happen with many, it's a sequence of, low installation pseudo curves so that you see a transition. But for the other case, it's enough that you see strong forcing that just pushes immediately the system off. So, of course, the question that you put in the base is also relevant towards how much is the height of the barrier, right? So how much do you have to jump across it? I don't know if maybe there is, but I don't know if they're realistic.
Well, it feels also a bit dangerous, all these arguments, because like it's easy to envision scenarios like a nuclear winter or maybe in a meteorite or volcano eruptions that lower the solar constant, but making it higher is probably very, very difficult. So we should only flow in the cold direction, right? Once we're cold, it's very hard to get out again because you will not have an unusually high solar activity.
Yeah, and this thing has happened in the past. At least that's what.
Yeah, but how did we get out then? Not via solar constant.
No, but the solar constant. It's probably from extremely high CO2 content into the atmosphere. This is probably how the system escaped. So it happened into the Neoproterozoic era. That was like 600 million years ago, probably twice. It's not sure if it's like it was globally glaciated or if it was partially glaciated. So maybe there was a band into the equator that was ice-free. But the idea is that probably, and even through volcanoes, so volcanoes can sort of unleash a lot of CO2 into the atmosphere.
Okay.
Yeah, and another thing just to mention about the real snowball Earth is it's fun to think about what the ocean must have looked like, because it wasn't all the way frozen. So there was still ocean dynamics. Heat was still being transferred. How? It's a good question.
So that's a very good point, because in the published version, the ocean we used, it was a slab ocean. So in the terminology, that is not a real ocean model. It was just a 50-meter sort of layer that could indeed transport heat, but still was not realistic. Then I tried for a real ocean for the particular model that was like 5,000 meters deep with, it had all the topography. And really the result was very, very similar. The only difference was that because of the ocean dynamics, you just have to persist more. Okay, the ocean dynamics are not as fast as the atmospheric dynamics. So even though I got this same profile again, and the warm state was now even deeper, the point is that the system is much slower because of the dissipative nature of the ocean.
Nice, that makes sense. That's cool.
I wanted to ask regarding the Levy processes.
Yeah.
I actually really like those, so
Thank you. And
ask a lot of questions. But the first question I have, was this motivated sort of by theoretical curiosity, what would happen, or is there some data that indicates that maybe a jump component to the stochastic process is a good model, because that's actually what's happening with the stochasticity in the system?
Yeah, so so one of the, I mean, I'm not currently an expert in this, but one of the first indications that there's something to Levy kind of, Levy noise into the geophysical context. It was by Ditlevsen about 20 years ago, that sort of associated the there are some events, geophysical events in Denmark. I cannot spell the name. But basically, the signal that they studied there, the differences of the signal clearly fit a jump profile. That was the first time. So it kind of seems that it is relevant in this case. And what we say is that it could also be relevant to study both. So have a signal, so have the perturbation that has both a Gaussian component and a Levy component. That's the idea. And of course, here we wanted to also understand to which degree concepts from additive Levy noise, which by the way are not, I mean, in the geophysical community right now, they're not heavily used. But we wanted to understand how relevant they are, for instance.
So this was exactly the next question, sort of in some way, the Gaussian case and the Levy case are sort of too extreme so in a totally different field, namely in mathematical finance, people sort of have been thinking for quite a while about how to combine those effects. There are many ways of doing this, but two basic ways are, one way is to say, I just look at a combined process. So my process has a Brownian part, Brownian motion part, and a Levy part, and see what's happening. And again, I'm not going to, however I scale my system, really to the limit epsilon going to 0, but let epsilon be small, but still a finite size. And in this way, I should have a combination of sort of the effect of the landscape that affects the sort of instantonic part of the Brownian motion, and the effect of the nearest, what's the nearest place where the Levy can jump to. And I think, but I think this has not been, at least to my knowledge, really carefully explored in sort of the full realm of this idea of looking at the landscape and all these ideas. The second alternative approach is to try to construct stochastic processes based on tempered Levy processes, where you start to cut to temper, for instance, with an exponential function or something like this, the very, very fat tails, and in that way, sort of to capture these parts. Which of those do you think will be more interesting in the sort of the?
Of course, the latter one. The latter one is also more physically relevant, I would say. Of course, if you have, it's here I didn't mention, but the Levy was truncated. We didn't overdo that. Otherwise, the system explodes. I would say the latter one is highly relevant. And something that I didn't mention is that, again, why we use noise is either, for instance, we don't know subgrid scale processes, and we put some noise to just sort of simulate them, or we want to sort of simulate events. And I think Levy, kick events, jump events, could potentially be of high relevance for this kind of studies. And I mean, I don't know how if it's relevant to the climate change problem, because the climate change problem is put differently. But on the other hand, if you just look at the time series of, you know, the CO2 content, it's jump in the CO2 in the last 100 years of, who knows? But no, it's a different problem.
So how much is that? No, I mean, it was surprising that this Arrhenius law type scaling went through completely nicely. You say instead of 1 over epsilon squared, you get 1 over epsilon to the alpha. That just came out, and it came out to like 3 significant digits or something.
Yes. So this was.
I mean, I have never really carefully thought about that. Is that known somehow generally that this should be the case, or is it known that it shouldn't be the case?
So this is this is solved formally for the infinite dimensional problem for additive noise, and very recently actually. But it's not, so it's an open problem for the case of multiplicative noise. So the fact that it, we demonstrate that it works here, we didn't expect, could, I mean, what we end up, it could potentially mean two things. So either this is a system which is, a subclass that sort of falls into the category of where this law holds, or there is something general, and it could be, because basically that was the same story with multiplicative and additive noise for linear processes. Also there, the original some of the original, for instance, prediction for additive noise under Gaussian perturbations could eventually be applied the same for multiplicative noises as well. Of course,
I didn't even realize. Oh, sorry, I don't want to interrupt. There's such a high lag that I always end up interrupting people. Go on.
No, I mean, of course, there are many details on how you discretize then the noise, and that between whether you use the types, but yeah, in our case we just used an Ito discretization, and it was quite consistent. Yeah.
So you said it was recently derived
Yeah.
that this scaling must hold in additive noise. Only recently. What is this? Like when and where and who?
I can send you.
Do you know?
I don't. I think we cite into this. No, I mean definitely cite.
Yeah. Okay. It's maybe enough. You
it's
said you uploaded yours a week ago.
Can you? Maybe I'll send around. If anyone is interested in the archive, and then we more cite everything.
So to clarify, you're talking about the theoretical result that says that you expect some kind of Arrhenius law for Levy processes, additive Levy processes.
Yes.
And you are surprised that you also observe it despite your noise being multiplicative. That's what you're saying.
Exactly.
So it must mean something like actually the quantity is roughly constant, yeah? Like the...
In the sense, you mean a constant in the... you mean for the noise?
You mean you do change? I don't know what the prefactor of noise was exact. Sorry, you say it's multiplicative, but if the quantity itself doesn't change drastically,
yep,
it multiplies, but it's roughly a constant, right?
Yeah. So you mean the prefactor, so the whole factor here, right? That so mu tilde, let's say.
Yeah, I think I'm just saying I have a double well in X with multiplicative noise, but I'm jumping between X equals 100 and X equals 101. Then I will not see much of the multiplicative noise because.
Okay. Yes. Yeah. Sure.
And you are in temperature, and it's between 250 and 300 or so. So maybe you don't see much of the multiplicativity of it.
So exactly. So could be the particular problem.
So I had one more a bit technical question about the Levy. So on the previous slide, the slide you showed before.
This one or?
And the one that says that you exit through the nearest region on the Western boundary. So I was wondering if that means, so kind of two questions. So one, what does nearest mean? There should be some metric, and I'm not entirely sure what would be the metric for that. And then also, I mean, here it seems like it also goes on the edge of the invariant measure. And I don't know if that's a coincidence or it's always like this. I don't see why it should be like this, but so I'm wondering what's known.
So in this example, so for the first question, actually, it's a little bit tricky when we look under this projection anyway, but indeed the signal coming from, you know, this part indeed only comes from the escapes. Now, of course, we didn't go ahead to, you know, measure the Bayesian, you know, the exact Bayesian of attraction. That could that is possible by other methods. So in principle, one can find the Bayesian boundary, and then could in principle find through an appropriate L2 norm the, you know, the distances. And so of course you know, this comment here, this remark that it exists in the nearest region, it follows what we know for Levy jumps in general, and sort of generalize here for this sort of infinite dimensional problem.
I guess I'm asking, so first, if I'm not sure I understand the statement. You're saying that you're exiting through the closest path to the separatrix, or you're saying that it's okay. And then, okay, so that I understand. But you're saying that the feature that it's edging on the boundary of the invariant measure as you're projecting it is just like just a coincidence, or it's you also expect it to. So what's the intuition behind it going on the edge of the invariant measure?
So for one kind of transition here, going from this, because I guess you're referring to one exiting the worm, going to the snowball. The other one is a bit different. But what is happening is that, think of it like this: there are jumps that sort of try to escape, but they're not sort of permanent enough to follow a Gaussian escape. So they might go upwards, okay, or they might go like this way, but they're not going to escape, because that needs a sequence of high jumps. But if it just happens that, because always for the Levy noise, it's just one instant that you get a strong jump, it's almost impossible that the next, you know, the next random number that you draw is going to be same as it's the red event. So most of them is just one kick, and then then it's just again fluctuations around the mean value base. So I assume that what happens is physically that, you know, it kicks, it goes upwards, then it relaxes again, kicks upwards. But then when it comes a strong jump, it's one of those events that it will kick it from this way, okay, which is nearest.
So you can think about it as a billiard, basically. Is that that you're going along the edge?
Maybe no, because I trying to think of the fact that in one case, in one set of jumps, they are not high enough, so they sort of meet the walls of the boundary. And in the other case, there are jumps high enough that directly cross the boundary, because they don't see the boundary in some sense. So I see it sort of energetically. I'm not sure if this is the right way to see it, but maybe the Tobiases are more relevant, can put some picture here.
So you say something like uphill Levy, you don't care about the dynamics at all, right?
Yeah.
Yeah, so that's definitely true in the epsilon going to zero limit. But if you have a little bit epsilon, if you have a little bit of Brownian motion on top, things can change. And I think there's a whole regime that, at least to my knowledge, is has not been at least extensively explored. I think, and I think it's right at the right time, where people are actually getting interested in this in a whole variety of fields.
Yeah, and it's extremely important. We noticed in both studies, in both kind of noises, to keep it on the weak noise limit. Otherwise, the system seems to sort of break. The deterministic attractors do not correspond to the stochastic attractors. You start to get different. I mean, you definitely get different outcomes from the theory as well.
Exactly.
So, I mean, I think we have lost a bit track of time, which is of course fine, but maybe we should open up for general discussion as well if people have still questions.
That's true. I should also
the other speakers, and maybe thank Georgios again.
Absolutely.
Thank you.